Hello, I'm Sourav. Today I'll be explaining DNA computing with my PPT. I'm from Institute of Engineering and Management from CSE third year section B. My roll number is 240. Let's move forward with the DNA computing. Firstly, we would talk about the DNA. What are DNA? Here in the list of modules we'll be following the introduction to DNA, Adelsman's experiment, application of a DNA-based systems, DNA-based computers versus the conventional computers, and lastly we would be concluding with a proper conclusion. What are DNA? As we speak, DNA are found everywhere. They carry a huge mass amount of data, which can exceed up to X terabytes. X terabytes. It's really big. So let's move forward with the proper definition of a DNA and what are DNA actually. Introduction to the DNA. What is DNA? As we speak, by the definition, a DNA is an abbreviation for deoxy deoxyribonucleic acid. DNA contains a genetic blueprints of a living creatures and organisms. DNA contains the instruction for assembling cells in the body. Every cell in our body has a complete set of a DNA. Each and every DNA are unique and for each individual. So let's move forward and find out what are the DNA structures. So in the PPT, you see a picture is there of a DNA, and in this picture we see the the sites that wraps up the DNA, which we call as the sugar phosphate backbone. Ladders that is inside going inside the slides are the complementary base pairs with the adenine and thymine, guanine and cytosine are the pairs that construct a DNA formation. As we see, the base pairs contains weak hydrogen bonds which holds and stands together to make our proper DNA. Let's move forward for the next slide and let's see what are the silent features of a DNA. The silent features of a DNA, if we speak, we firstly in our mind that comes the DNA replication. The replication is quite like, in simpler words, it's like cloning. A DNA replication is the method by which the molecule can form an exact replica of itself, and the DNA gets embedded in both these daughter molecules. So we see that the clone that are produced by we are producing by the DNA, make like daughter cells. They are the exact replica of a DNA. A DNA extraction, if we speak, a silent feature. In this feature, we find that it is a method. It is a method. It is possible to separate and bring together different strands of a DNA that are of the same type. So we find the same type of a DNA by doing the DNA extraction. The DNA annealing. In this method by which two DNA strands can be brought together. We bring two DNA strands and then we pair together with a melted form of one single entity. So these are the silent features, features of a DNA. Uniqueness of a DNA. A uniqueness of a DNA is extremely dense information storage. As we see and as we know that the DNA are unique for each and every living organisms, and they store a huge mass amount of data, and they are very small, very tiny. It can you can say that a DNA, it's like a sugar cube that holds a mass amount of data, and it's very cheap. Parallelism and energy efficiency. In extremely dense information storage, we do the calculation by 1 gm DNA equals to 1 into 10 to the power 14 bits. And in parallelism, the exact calculation we do by doing 3 into 10 to the power 14 molecules at a time. So that's a huge number. And energy efficiency, we see that 1 joule, and that is equals to 2 into 10 to the power 19 operations. So that holds a really a huge amount of a data inside a DNA. So then now we move forward to the Adelsman's experiment that we have conducted here. By that experiment here, it's about a salesman who is moving through different cities, but he can't cross path with each city twice. So the experiment speaks how we compute a DNA in a network of cities, of a network of cities where the salesman struggles. So let's Adelsman's approach. According to Adelsman, he believes things like DNA computing will eventually lead to the way to a whole molecular revolution, which ultimately will have a very dramatic effect on the world. It was told by Adelsman, and it was his approach. So previously, what I was saying about the experiment that I have gone through in while doing this PPT is Hamilton's direct path problem, which is known by the HDPP. The problem statement. Let's see the problem statement. The consider a salesman who has to travel number of cities on his daily basis. Now the problem is to find for him the working uh, fastest route without taking through the same city twice. So the salesman problem that he can't go through the same city twice for his journey. So let's see the problem. Here we have included some cities like Delhi, which is the source destination for going through all the cities like Mumbai, Mangalore, Kochi, and the Kolkata. Kochi is our final destination. Kochi is our final destination city. So let's see how we find out the path to reach the final destination. The solution of this problem is by doing the solution can be found out by using the replication property of a DNA. So previously what I told that replication is like cloning, like making one daughter cell and daughter DNA and the other daughter DNA are exactly alike. So we are doing the replication of a DNA. Several operations can be checked at once as DNA performs the parallel processing. So far, this method has been successful up to 15 cities. This method can be, not can be, this method has been successfully made for the 15 cities. And with this advancement, most daily number of the cities are to raise up. So let's move forward to the problem. Then we find the Adelsman algorithm. What Adelman had followed for this kind of a situation in the DNA computing for the salesman. We generate all possible routes. We have to generate all possible routes, select itineraries that start with proper city and end with the final city. The final city was Kochi, and the source city was Delhi. The gel electrophoresis is the process method. Select itineraries which contains each city only once. So as I told, each city we are conducting by this for the salesman, the city can be traveled by only once. So the general possible routes are here as follows. We encoded the cities with some codes, and the city names are Delhi, Mumbai, Kolkata, Mangalore, and Kochi. Let's move to the city and solve the problem. Generating all possible routes. Now we encoded itineraries by connecting the city sequence for each routes exists. For example, Mangalore has a city code by the city code which is CTACGG. From this city code, we would take the last three codes of this last three codes of the Bangalore city code, and we'd be tallying it with the destination city Kochi, which has the code ATGCCG. The first three code we are taking it from the front. Let's say S1 is the path to reach from Bangalore to Kochi. So S1 is the path to reach Bangalore to Kochi, and S1 equals to CGG ATG, where CGG is the Bangalore city last three codes of the DNA, and the destination city last three codes of the DNA has been added up in the string ATG in the S1 string. Now we compute S1 bar equals to the GCCTAC, which is now the complete DNA. Now this is the complete DNA that we find for this solution. Now the Mangalore to the Kochi has this GCCTAC as the DNA standard. Similarly, we find the codes for all paths in the possible routes. And now we would be explaining for each cities how it follows the path, and finally the salesman reaches to Kochi to his final destination. Select desired itineraries. The next step to select desired itineraries that start and end with the correct route strategy is to selectively cope and amplify only that DNA which starts with Delhi and end with Kochi. So, as I said earlier, Delhi is the source city and the Kochi is the destination city for this DNA computing problem. Gel electrophoresis. Sort of the DNA by the length and select the DNA whose length equals to 5 cities. Generally, the DNA is negatively charged molecule having a constant charge density. The gel slows down the passing of a DNA depending on the length, therefore producing the bands. The technique used is to gel electrophoresis, which is a proper technique to make a proper DNA from this um, the DNA stand we are creating. It is used to differentiate between the DNA molecule having different lengths. So let's move forward to the next slide and find out what are the gel electrophoresis diagram. What is a gel electrophoresis diagram? Here in this picture, we find a blue color, which is the DNA fragments. So these are the DNA fragments, and the gel particles are the red balls-like structure, which is in this pictorial PPT. And here, this the DNA fragments goes under a process in the gel electrophoresis diagram, and lastly end up with the parallel DNA diagram. The solution for the paths encoding. The cities that we conducted this DNA um, this DNA for the problem statement solution is to Delhi to Mumbai, Mumbai to Kolkata, Kolkata to Mangalore, Mangalore to Kochi, and we will be cross passing the path only once. The path symbol we have taken as S1, S2, S3, S4 respectively, and their codes are we can see in the screen. So let's move forward and compute this DNA computing. Selectively itineraries which contain each city only once. So the salesman who is moving from the source destination Delhi by the route of S1 bar, which is the path only cross passing only once with Mumbai, then S2 the cross path for Mumbai to Kolkata, from Kolkata to Mangalore, Mangalore to Kochi, the final destination. Like S1, S2, S3, S4, the path only crossing only once, so they can't be cross path twice. We can't do the cross path twice for this DNA computing problem. So the application of DNA is based on the computing, and each time we see the DNA has a very unique way of showing showing the problem, where the salesman only can cross path each city only once, but he can't cross path the same city twice in this DNA problem. The application of a DNA based computing. So now we will speak about the application of a DNA based computing. Solving NP complete and hard computational problems, and it stores associative memory, a DNA to DNA problems, a DNA sequencing, a fingerprinting, and a DNA mutation detection. These are the application of DNA based computing. Let's move forward for the DNA based computers versus conventional computers. We will be distinguish between the DNA based computers with the normal conventional computers that we use in our regular basis. So DNA-based computers versus conventional computers. Our DNA-based computers can do billions of operations simultaneously. So it can do billions of operations simultaneously, and it doesn't fall in a so it doesn't feel tired. And in conventional computers can do substantially fewer operations in simultaneously. So according if we distinguish between DNA based computer and the conventional computers, we see that it can do billions of operations simultaneously, whereas the conventional computers on the other hand can do the fewer operations simultaneously. A DNA-based computer can provide huge memory in a small space. As I told that, like a DNA is like a sugar cube, and it can store a massive amount of a data. So we see it can hold a huge amount of a data in a small space. A smaller memory for the conventional computers. Conventional computers can hold a smaller memory. It doesn't require a huge memory as the DNA-based computers. Setting up a problem may require considerable preparations for the DNA-based computers. And conventional computers setting up only requires a keyboard input. Whereas the DNA-based computers, if we see, are sensitive for chemical deterioration, encoding, and algorithm like things, um, problems. And whereas the conventional computers are based on the electronic data, which is vulnerable and can be backed up easily. Whereas the DNA computers needs a huge amount of time and patience to get a backup from the cloud or something else. A DNA computer has, it's like it can be stored in a hard drive, and so DNA computers are not backed up easily like the conventional computers. That are the basic distinguished points that I have prepared for this PPT of a DNA computers versus conventional computers. Now we would be ending up with a conclusion, as I said, and now the as now we the conclusion, if we speak, a DNA is the generic code of a life itself, has been the molecule of its century, and certainly the next one. The future of a DNA manipulation is a speed, automation, and miniaturization. Perhaps it will not be good enough to play games or surf in the wave. It Playing games and surfing in the wave is basically for the conventional computers, and the DNA computers are generally mm, go with the study problems like making up a logic, doing encryption, generic programming algorithms like automata, and lots more things. So uh, with the conclusion, we go with the things that we traditionally computers are good at are playing with games and all these stuff, but it certainly might be used with the study of logic, encryption, generic programming, and the algorithms, automata, and lots other things that haven't even been invented yet. So this non-invented um, this non-invented things that about to come in the next coming days are would be used with the DNA computing to do this kind of study for the DNA computing, doing logic gates, encryption, and lots other things. Therefore, we conclude this session with this last point of our conclusion. Therefore, it won't be an aggression to state that DNA computing is definitely the technology to watch out for the coming years. Certainly, here to say that DNA computers in these coming years would be much more exclusive in the coming years, and we will see how the DNA computing progresses and make a huge approach and make a huge approach and be in this programmatic study. So the salesman problem we have solved, and there we find some um, mm, uh, problems with roots. So feel free to ask. if there is if you find any problems with the salesman problem. And now I'm ending my session, PPT session. Thank you for being with me for this so long. Thank you.